Okay, let's begin. So, last time, we finally learned what probability is, and we saw that we defined what's called finite, emphasis on finite probability. So we define the probability of an event A to be the size of the set A over the size of S. S equals, it's a set, and it is called a sample space, and describes all possible outcomes. And A, this is a subset of S that we care about at the time. And we define the probability of that event. It's called an event. By actually finding the size of the subset, dividing by the size of the sample space, and we define that to be the probability. So it's the number of ways to get what you want divided by the total number of things that could happen. So what I want to do is just show how we're going to apply this formula in various contexts, because at any given time when we're looking for a probability, this is going to be how we want to think about it, not just by what makes sense or feels intuitive. So what I want to do is we're going to go through a few examples, and I type them up. And this is posted on the class web page as usual. Pass these around. Pass these around. Pass these around. Pass these around. We're going to go through a few of them. And when we hit problem 8, we're going to have an entirely new concept that I want to talk about, and then problem 10 also refers to an entirely new concept. But let's just get through the, make sure that we know how to apply this idea. It's a very important idea. We also saw, and these are going to become relevant, that the probability of a union is the sum of the probabilities minus the probability of the intersection. We also saw that the probability of an event is 1 minus the probability of the complement of the event. In other words, that complement, remember, is everything that's in our universal set, which is the sample space, that is not in the set A. So we're pretty much looking at how many things could happen other than what we actually want to happen. And we can actually sometimes get to what we want by doing 1 minus that. Yeah.
Can we get one more?
And I believe that's all the formulas I told you so far. We're going to actually talk about some new formulas today as well. But let's make sure that we can use these basic formulas that we have so far. So let's actually do example 1, where we're going to start. I probably won't do all the examples, but I'll just use a few. Let's start with example 1. Probability set 1 and out. 1. Okay. So we have a fair coin. That just means it's a coin with the heads and tails. They're two different sizes, and normally heads and tails. You take a coin, you toss it 3 times, you record the outcomes. What is the probability that you get exactly 1 head? Okay, so A. Toss coin 3 times, thrice. Probability of 1H. How would you actually think about this? How would you set it up? Go, now go. Try to use that formula I gave you. How would you set it up? It's the first thing you want to do. Yeah?
We'll find the sample space.
Sample space. We need to figure out what is the sample space? What are all the possibilities that if I were to toss a coin 3 times? So that's the first thing you want to conceive of. Now there are multiple ways you can think of the sample space. You are allowed to be creative here, but give me one way. Yeah?
So you think of it in stages, so 3 stages and 2 possibilities for each, so it'll be 2 cubed per stage.
If you think of it in stages, that would just describe one possible scenario, right? So if you were to think about all possible scenarios, you want to say a set of stages, or maybe a set of, what would you want to express the stages as? Well, you can probably do a set of coordinates, right? Like A, B, C, such that A, B, C are, they can be H or they can be T, and A is the first toss, B second toss outcome, C third toss outcome. Right? So I can conceive of my sample space as that set. Notice that I'm not going to write out all of them. So I could have heads, tails, for example, or I can have heads. I could have a bunch of things, okay? Now, the question is, how many things would I be able to have? Well, now's where you kind of think, well, this is in stages. Think of each toss as a stage. How many options do I have here versus there versus there? Well, you have 2 options in the first case, heads or tails, 2 options in the second case, heads or tails, 2 options in the third case. So you know that there are 8 total scenarios that could happen. Now, we want to talk about our event. Our event is going to be a subset of all total possibilities. So what would our event actually look like? How many ways can you get one H? There are literally 3 ways. Either you're going to get an H on the first one, but not the other 2, or you're going to get H on the second one, not the other 2, or you're going to get H on the third one, not the other 2. So, the size of the event that I care about, there are 3. This means the probability of getting A is going to be 3 out of 8. Probably have 1 head. This is one way that you could have done the problem. I'm going to actually, for each example, I'll probably do a couple ways, because there are multiple ways you can think about it. So it's not just one set way, bless you. You do have some creativity on how you're going to think about the scenario. But so far, like in theory, I'm not saying you prefer to do it this way, but do you understand what just happened? Okay, so I conceive of a way to talk about all possibilities. Then, based on that, I'm going to look what subset of this would give me what I want, and then I count the both sets, and I divide them in the order that the definition requires. Here's another way you could have done it. So maybe you don't like thinking in coordinates. You could have instead, option 2, think of it as a tree diagram with stages. So you have stage 1, which is the first toss. You have stage 2, which is the second toss. You have stage 3, which is the third toss. The point here represents the beginning. Now in the first stage you can have boom, boom. You can get a heads or a tail. And then once that first flip is done, you can have boom, 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 boom. So you can have a heads or a tails on the second go, even based on whatever situation you have. And then that would end the second stage, which is the second toss, and then you can have boom, 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 boom. So you can get heads or tails, heads or tails, heads or tails, heads or tails. You would realize that at the end, counting how many arms you have at the end, you'll notice that there are 8 total possibilities. And now all you do is you count all the possibilities that can give you what you want. So, for example, to get one H, I just need to go along an arm where there will only be one H along that arm. So let's say I can flip and I can get the H right away, but once I get the H, I can't get him again, so I'll have to go along that arm. And if you notice, going along this arm, that's literally the only path I can take, because any other path I take, I would get more H's. So the other option is I can go along, get a tail first, then get heads, but once I get that one H, I would have to choose tail again. So that's another option. Or I can get tails, I can get another tails, but I need to make sure I get at least one H. So there are 3 arms that give me what I want. So I can conceive of my sample space as a tree diagram, and then I'm just counting the branches that have what I want. So we have S is, the 8 branches. My A is a set of 8 branch tree. My A would be there are 3 specific branches in the tree. So this would mean that the probability of A is going to be 3 out of 8. 3 out of 8. There's another way you could have visualized it. There's another way you could have visualized it. I told you guys how to fill out a table when you have a very specific number of options. So the multiplication rule is going to tell you that you should have 8 options. And so what you can do is 1, 2, 3, 4, 5, 6, 7, and 8. So remember, when there are only 2 options, you switch every power of 2. So in the first situation, you are going to switch every 2 to the 0 times. Here you're going to switch every 2 to the 1 times. Here you're going to switch every 2 to the 2 times, and etc. So 2 to the 0 is 1, which means you switch every row. So you start out with H, you switch to T, you start out with H, you switch to T, you start out with H, you switch to T, H, T. Switch every 1 time. So this would be, say, the first toss. And now I'm going to switch every 2 times. So 2 H's, 2 T's, 2 H's, 2 T's, until I get to the end. That would be options for the second toss. Now I'm going to switch every 4 times. 4 H's, 4 T's. That's my third toss. That would ensure that you would hit all possibilities. And again, similar to the tree, you're going to pick the possibilities that you want. How many rows actually have 1 H in that row? Well, there's going to be this one, this one, and there's going to be this one. So I have 3 rows in an 8-row table that will give me what I want. The probability is going to be 3 out of 8. S is just an 8-row table. A, 3 rows give me what I want. This means that the probability of A is going to be 3 out of 8. We're going to solve the problem that way. Many ways to conceive of it, and this is what I meant by when I set it out. When you're talking about the sample space, you can be very creative in how you want to think about it. Just make sure that you are thinking about it. A lot of times we jump into probability, you just decide to start multiplying fractions. Oh, it's going to be a half times a half, right? And yet you have no reason why you're even saying that. You do not want to be in that boat. There has to be a very definite, specific way that you're thinking about the sample space. that will describe all possibilities in equally likely terms. Here's another option. Now, there will come a point where the tree diagram and the table form is going to be cumbersome. So if you're in a situation like, for example, if you're in the situation of like poker hands or something like that, remember there were 2.5 million options. You're not going to draw a 2.5 million rowed table. Not very efficient. You also don't want a 2.5 million branched tree, right? So in that situation, option 1 would probably be something that you can do. Just conceive of a set, make sure you know how it is, write out a few examples. So, okay, I fully understand how the elements of the set would look. And then you can find the size of the sets using counting arguments. Or you can just use counting arguments in general. So option 4 is completely formula-based. You don't have to visualize anything, you're just going to use the formulas to be your guide. So you can think of find the size of S via multiplication rule. So I understand that each situation is going to be a 3-staged experiment. There will be 2 choices, 2 choices, 2 choices, which gives me 8 total choices. Now, to know that here I want 1H. Now, how would you conceive of that as a formula? What you would think, there are 3 positions. I want H in 1 position. Now the important thing is, you want H in 1 position, don't care about the order it comes in. I don't care if H is in the 1st or the 2nd or the 3rd position. This means, how many ways can I have my event? I have 3 positions. I care about one of those positions being filled in a very particular way without order. How many ways can that happen? 3 choose 1, that's a combination. That's 3. I am going to just have a 3-positioned experiment, and I just want to make sure one of the positions are filled in a particular way. That's 3 out of 3 options, choose 1 at random. That's 3 choose 1, and then option 4 continue. So then we know that the size of A is going to be 3. This means that the probability of A is going to be 3 out of 8. Many ways to get to the same thing, right? You can be creative. You might like drawing trees, you might like doing tables, you might like thinking just in terms of formulas. So you have options. Some of them lend themselves to problems easier than others. I mean, here there were just 8 total options. Actually drawing a diagram isn't that bad. When you have a lot more options, you probably wouldn't do option 2 or 3. And option 1 or 4 would probably be how you go. But the point is, you have to have a very specific way to think about the situation. Don't just run into it and just think, oh, well, you know, 2 options, so heads is 1 out of 2. Do I just multiply a half times a half times a half? Like, no, that's just you just not really thinking. You're just like, well, I know the probability of getting heads is a half, so a half is going to be in the answer somehow, right? Not necessarily. Right? That's how you get in trouble. Make sure that you're thinking of the sample space in a very specific, definite way that has all the features that you want from a sample space. And then you figure out, based on your preference, how you want to go about counting the sample space. So it's a lot of, we got a lot of stuff out of example 1, part A. So hopefully, now for me personally, I don't particularly prefer one method over the other. So it depends. Sometimes I'll draw a tree, sometimes I won't. But you should be aware that pretty much for any probability problem I solve on the board, there are other ways to get it done just as accurately, just as using a different method. So,
One party.
one part. Exactly 2 heads. Now, I'm going to do option 4 here just because it's the shortest one to actually write down. So, each experiment has 3 stages with 2 choices, 2 choices, 2 choices. This means 8 total choices. Now we want 2 positions to be H. Order does not matter. This is equal to 3 positions, choose 2 at random to be H. So 3 choose 2 is going to be 3 times 2 over 2 times 1. There are going to be 3 total ways for that to happen. And so this means the probability of getting what I want in this situation is also 3 out of 8. So you're just as likely to get exactly 2 H's as you are to get exactly 1 H. So if somehow this was a gambling game and you're with your friend and you're putting some money down, you know what, I want to bet that there are 2 H's, and your friend goes, no man, you should bet that there are 1 H. You should know that your friend has no idea what he's talking about. Like, no, it's the same likelihood. You're just as likely to get 2 H's as you are to get 1 H. Let's look at 1C. At least 1 hit. So this one is important. You should recognize that the phrase "at least" shows up very often in probability and statistics. This just means if it says at least 1. Doesn't have to say 1, could have some other number here, but what this means is greater than or equal to 1. So whenever you see at least blah, it means greater than or equal to blah. These 2 phrases mean exactly the same thing. So this scenario is asking, what is the probability that we'll get 1 H or more, right? Can we get 1 or 2 or 3? And like I said, tons of options of how to do this problem. Here's one way we can do it. So you could draw the tree diagram and just count how many ways you'll have 1 H or more, or the table, count how many ways you have 1 H or more, or do the coordinates. But I'm going to use this as an opportunity to use one of the axioms of probability that I mentioned before. So note, the scenarios of exactly 1, exactly 2, and exactly 3 do not overlap. So that's the first thing you're going to notice. The second thing you're going to notice is that this means the probability that the number of heads is greater than or equal to 1, well, that's going to be the probability that the number of heads equals 1, or the number of heads equals 2, or the number of heads equals 3. And we had an axiom of probability that said, if each situation does not overlap, then the probability of OR is the sum of the probabilities. So this is going to be the probability of getting one head plus the probability of getting two heads plus the probability of getting three heads. And I do want to emphasize here that OR translates to plus only in the case that there's no overlap. So this, do not overlook this sentence that I wrote here, because that's not true in general. That I can write down because there is no overlap. So the OR translates to plus, or translates to plus if no overlap. Another phrase for that is mutually exclusive events, but I'll actually define that phrase specifically later on. Okay. So if I talk about any one of three situations that can happen, and you can't have two of them happening at the same time, I can't have exactly one H and at the same time have exactly two H's, right? So I can add the probabilities. Now the first two we actually found. That was 3 out of 8, and that was 3 out of 8. The last one, how many ways can you get 3 heads? There's only one way you can get 3 heads. So this one we didn't actually find, but it should be clear that there's one way to get 3 heads. You need H in the first stage, H in the second stage, and H in the third stage. And so, this is going to be 7 out of 8. It's one way to do it. I actually want to do this problem in another way, but I'll wait until you guys copy that down and then I'll talk about it. This is a really common way that someone would do this problem. There's another common way someone would do this problem. One isn't better than the other, it's just what you personally would notice or see or what formula you like to use. Here's one thing that you can notice. Note. So, if you happen to read a problem and what you notice is that all the situations described don't overlap, if that was the first thing that you noticed, this is probably the way you would have done the problem, and that is completely fine. But let's say you notice something else entirely. Let's say you notice that there is only one way to not get at least one head. What if that was what jumped out at you after reading the problem, which is actually true, right? So if you have a position where you're going to have one H, or you're going to have 2 H's, or you're going to have 3 H's, there are many ways that you can have combinations. So if there's one T, well, the T could be in this position or that position or that position, and or if there are 2 T's, the T could be in these 2 positions or those 2 positions or those 2 positions. Like you'd realize that you'd have to count several positions. In fact, for each one of these, if there's only one H, there are 3 different positions that you had to realize could occur. If there's only 2 H's, there are 3 different positions that you have to realize could occur. But if the situation of having none, right, which is the opposite, the no H situation, how many ways can that occur? Literally only one way. You'd have to have a T, and a T. Right? There's no options to think about in that scenario. Right? So there's only one option. So, let's say that's what jumped out at you when reading the problem. Here is how you would proceed. You might, so you realize the opposite. Of greater than or equal to 1h is less than 1h, which means 0 h's. Only one way. This means the size of not having what I want is one way. There's one way for that to occur. This means I can use the probability of what I want is 1 minus the probability of what I don't want. That was a form that we discovered at the end of last class. So this is just going to be 1 minus, what's the probability of the complement? Well, it's the size of the complement over the size of the sample space, which is 8. And 7 out of 8 would be your answer. So you could get to the problem that way. Get to the answer that way. And like I said, no one way is more correct than the other. You will have options. The important thing is, you're thinking about your sample space in a very specific way. You're not just running in, starting to multiply numbers or just divide random numbers. You first conceive of the sample space. Then you conceive of what you want to get. Ever so often, sometimes the thing you want can happen in many ways, but the opposite of that thing can happen in relatively a few ways, and you might prefer to count the ways to not have what you want, as opposed to counting the ways to have what you want. And then you can just use this equation to do that. You can find your answer in terms of figuring out the opposite. And that is using what we call the complement probability. So that's an important equation. Sometimes figuring out what you want is harder than figuring out what you don't want. And so you might go the route of, let's figure out that and then subtract it from 1. That's going to be our answer. Part D. At most 2. So, okay, so this is also a very common phrase. At most 2. That is going to translate to less than or equal to 2. That's what that means. So at least means greater than or equal to. At most is just another way of saying less than or equal to. So, also many ways that we could approach that problem. Let's use the complement way for no particular reason. So, the opposite of less than or equal to 2 is greater than 2. There's only one way for this to happen. Namely, we must have 3. Because we're only tossing the coin 3 times. We're in the scenario where we're tossing the coin 3 times. So the only way I can get more than 2 is having 3. We must have 3 each. Right? I must have the scenario where I have H, H, H. So this means the size of the complement, what I don't want, is going to be 1. And the size of the sample space is 8, which we figure out by the multiplication rule. I'm not going to do that again. Which means that the probability of the complement is going to be 1 over 8. Which means that the probability of what I actually want is 1 minus the probability of what I don't want. 1 minus 1 over 8. So 7 over 8. Now for these problems here, it's a coincidence that we keep getting the same answer for different things, just that when you only have two options, there's only so many ways things can actually work out. And you could count this directly, right? So if we say at most 2, that means you could have 0 or 1 or 2. There's one way to have zeros, there's there are 3 ways to have 1, there are 3 ways to have 2. And then you can add those all up. That's 7 ways total. And out of 8 possibilities, you can get 7 out of 8 directly. But yes, we have options. And I wouldn't really go about thinking of one option as being preferred to another one. That's not how I would think about it. Just that whatever you happen to notice first, take advantage of it. Because at some point, intuition is how we're going to figure things out. You just want to make sure that your intuition is trained. It's not just random intuition. It's a very intuition that goes down a specific road. So once you start thinking in a certain direction, you just have to figure out, okay, if I want to go down this road, what is the right way to go down that road, right? Let me make sure I set things up. Let's jump to problem 4. You toss 2 fair 6-sided dice. Find the probability that you roll a sum of 7. Okay, go. How are we going to set this problem up? Yeah?
That's the other one, you find the same space first.
Yeah, that's always what you do first. It's just that how you want to go about finding this one. So probably what we could do is just think of a set of coordinates where A is outcome of the first die, B is outcome of the second die. Now I would say coordinates here because I don't want to think of these as sets, because if they have the same number, we're going to lose that information. So I can think of my sample space as being numbers like 1, both dice give me 1, 1 gives me 1, the other gives me 2, 1 gives me 1, the other gives me 3, 1 gives me 2, the other gives me 3, etc. Right? So there are going to be a bunch of things here. Now, how many possibilities are there? $36. I don't randomly come to the answer 36. There's a very specific schema under which I'm thinking. Okay, just think of this toss as a 2-stage experiment, where one stage is choosing the number on the first die, the other stage is choosing the number on the second die. There are 6 choices that can happen here. There's 6 choices that can happen here. This means that there are 36 total choices by the multiplication rule. Now I want to know, A is going to be a subset of my sample space that includes the possibilities that I care about. Now the possibility is that the sum is equal to 7. What are the possibilities for the sum being 7? Well, I can have a 1 and a 6. I can have a 2 and a 5. I can have a 3 and a 4. And then literally all the switches, right? So 6 and a 1, 5 and a 2, and a 4 and a 3. The size of A is 6. This means the probability of getting a sum of 7, 6 out of 36. One way to do the problem, totally valid. Above board, sanctioned. Another way to do the problem, which if you set it up this way, And it's a very common with the 2 dice scenario. But once you get more than 2 dice, this now becomes a lot harder. But once you kind of set this up this way, it's going to be easier for you to figure out all the other situations. So the other way is to actually do the table. So I showed you guys how to set up a table with dice before. So you put the option for die 1 along the top, 1, 2, 3, 4, 5, 6. I'm going to create a table where I'm finding the sum. And then the options for die 2 goes on the other 1, 2, 3, 4, 5, 6. Now, right away, you'll be able to visualize. You'll actually visually be able to see that there are going to be 36 total options because you can end up with a 6 by 6 square. So there will be 36 boxes here. Now, I'm going to fill these in with the sum of the 2 numbers. So the 1 plus the 1 is 2, 2 plus 1 is 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. These are all the options. So these numbers aren't in there. This is the heading. So there are 36 possible ways for the sum to happen. And what I would do is count the number of ways for the particular sum I want to happen. So there's 1, 2, 3, 4, 5, 6 ways to get a 7. So once I draw that diagram, I'd be able to see. So for part 4A, I know that the size of the sample space equals the number of entries in the table. That's going to be 36. The size of there are going to be 6 entries in table. So that's a subset of the full table. And this means that the probability of what I want is going to be 6 out of the 36 entries. The nice thing about that is you can immediately use that table to talk about the other ones. What is the probability that you roll an even number? So basically I would go to this table and I'm going to look at all the possibilities of getting an even number. Let's do this in red for contrast. Yeah.
So with like back to 4A, so when we found the size of A, we just counted the possibilities. If it was a larger set, is there like an algebraic way to find the number of possibilities for the set?
Yeah, counting techniques. Permutations, combinations, multiplication.
So what would that be?
What do you mean?
Like what would you use? Like what counting technique could you find that sum without having to actually write down every single word?
Oh, you mean the number, to make sure that the numbers add up to a certain thing? Yeah, that is more like the 12-fold way thing that we were talking about, one of those ones. The thing that I mentioned in office hours.
Yeah.
So that there are ways to count how many ways you can add up to 2 numbers, given that you know the relative sizes of all the other numbers. But yeah, this is a nice way for dice. It's small enough and easy enough. With 3 dice, it immediately becomes harder, and then you can probably think about more sophisticated ways. I'll probably never ask you about 3 dice though. But okay, where are we? We are in B, where we care about the evens. So 2 is even, 4 is even, 6 is even, 8 is even, 10 is even, So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18. So here, the size of what I want is going to be 18. This means that the probability of what I want is going to be 18 out of 36. See, if you were to guess what the number would be, so if you wanted to have a bet on a single toss of the two dice, what sum is going to show up? What would you bet? Why? It's the most likely. Out of any other number, notice that the 7 happens along the diagonal. He will have the most occurrences. The next most likely numbers would be the 8 and the 6. They'll happen in equally likely number of ways. Then the 5s and the 9s will also happen equally likely, and so on and so forth. But the 7 has the most outcomes. This has the most appearances in the table. So that's what the bet would be. So there's a game called craps where it's a good thing to roll a 7 with the sum of 2 dice. It's one of the reasons why the number 7. That's very random. Not very random at all. It's actually a way for them to make you think you're going to have good luck. Let's throw them a bone. What's going on here? Which I'll talk about that a little bit later. About how gambling games make you think you have a shot. You know, 7 is actually the most likely. But it turns out 7 compared to all the other possibilities is not as likely. It just happens to be the most likely sum. But there are many other situations. Because there are 36 possibilities, 6 of them give you the 7, but there are literally 30 other ones that would not give you the 7. And so to just be aware of that, we'll talk about that a little bit more, but D, let's talk about D. Sketch a probability histogram. So this is a way that you can visualize probabilities. We'll probably talk about it a little bit later when we talk about probability distributions as well. But it's just a pictographical representation of the probabilities. So basically, it's when you plot the probability against the outcomes. So here are possible outcomes. Possible outcomes. So the possible outcomes are, the sum can be 2, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10, or 11, or 12. Okay, so we have, those are the possibilities. Now on this, on the vertical, we actually plot the probability of the outcome. So one possibility is to get a probability of 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, or 6 out of 36, which is the highest number. Now, how many ways can a sum of 2 happen? Well, 1 out of 36 possibilities. That's only one of the possibilities. Probability here is 1 out of 36, and you will put a bar with the height of the probability. For 3, you'll notice that there are 2 ways. For 4, you'll notice that there are 3 ways. For 5, you'll notice that there are 4 ways. For 6, there are 5 ways. For 7, there are 6 ways. And then it pretty much starts to go down from there because you increase until you get to the diagonal and then you start decreasing on the other side. And it's actually going to be a symmetric one, which is not all the time you'll see a symmetric one, but in this case there is a symmetric one. So that's what the probability of histogram will do. And you'll notice that in terms of any one particular roll, 7 gives you the most. However, comparing this to all of these, if you were to take all of these and stack them on top of each other, it's far more likely that you not get a 7. But you can also see the chance of getting a sum of 6 or 8 is the same. They are each 5 out of 36. Chances of getting a 5 or a 9 or a 10 and a 4, those are all the same. So this is what an histogram will look like. And they can have varying levels. This one happens to be symmetric. So, at some point we'll either finish all of these or I'll have you guys finish all of them. But I just wanted to show you some of the techniques on a couple of these examples. What I want to do now is actually jump to example 8, because I want to end the class with talking about a new idea to have your brains chew on for next time. So at the end of problem 8, I want to be able to derive a certain formula for you. So we're going to kind of proceed through this example in a somewhat a strange way, or just to kind of explain the thought process while we're doing it. You roll 2 fair 6-sided dice. Okay, so you're in the 2 dice situation again. You roll 2 dice. Find the probability the sum is 10 given that a 6 was rolled. So you'd probably start this problem the same way we started the last one. Figure out how am I going to think of the sample space. So I can just think of this as a set of pairs where the numbers can be 1 or 6, so 1 and 1, 1 and 2, dot, 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 and then I've got 3 and 4, or whatever, dot, dot, dot. And I would immediately see that the size of the sample space is 36 via the multiplication. So this is supposed to represent all possibilities. Wait. Hold the phone! Stop everything! We're given some extra information here, aren't we? Right? We're told that a 6 was rolled. How do you put that information into? What does that mean? Yeah.
So is this B a given B? So we're going to say probability. We want the sum to be.
Spoil it. Just like what does that particular
Yeah,
thing?
so it means that the sample space isn't.
The sample space changed.
It's 6.
This is in fact what happened with the 2 children problem, right? A couple has 2 children. What's the probability that they're both girls? You had one answer. If you know one's a girl, what's the probability now that they're both girls? The answer changed. Okay, if you know that the older one is a girl, what's the probability that they're both girls? The answer changed. Why did the answer change? There was a change in sample space. Once you're given information, what happens is now the total possibilities will change. So I know that not everything is an option anymore. I know for a fact that one of the options have to be a 6, which means this coordinate, for example, didn't happen. It's impossible. The new sample space, let B be the new sample space. So basically, B is going to be the set of all possibilities when one of them is a 6, or at least one, right? So what can we have in B? Well, 1 and 6, 2 and 6, 3 and 6, 4 and 6, 5 and 6, 6 and 6, or we can have a 6 and a 1, 6 and a 2, 6 and a 3, 6 and a 4, 6 and a 5. You wouldn't do 6 and a 6 again, that's already accounted for. There's only one 6, 6 in that table that we drew earlier, so that's where it would end. Now you'll notice that the size of B is equal to, how many things is that? 11. Now, if I said A equals the event sum is 10, A would be the set, well, 6 and 4, 4 and 6, 5 and 5. So here we have all this information. How do we actually put it together? What is going to be the probability that the sum is 10, knowing that a 6 was rolled? Yeah.
Well, if one of the die has to be 6, isn't 5, 5 not there?
Right. This guy is not an option. Now, how can you describe the set of options in terms of the sets that I just wrote down? So the event we want will therefore be, how can you describe the event you want? You can see it right here. The event we want is 6, 4, and 4, 6. We don't want the 5, 5 because I know one of the things have to be 6. But what is the relationship of this set, the set of these two elements? Yeah?
The two die add up to 10, given that one of the die is 6.
Yes, but in terms of the set relationship, how does that set? Yeah.
It's a subset
Subset of what?
of B.
Sure, but more specifically, how can I find that subset? Yeah.
It's A intersect B.
It's actually A intersect B. I want to look at all the possibilities that I have, not in terms of the original set, but in terms of who intersects with the new sample space. So these are in general the ways to get 10, but that guy doesn't intersect with anyone here, so he should be ignored. The intersection of A and B is what's going to give me what I want. So therefore, what we're going to have is the following. So the probability that the sum is 10 given that a 6 is rolled is going to be the size of A intersect B divided by the size of B by using our probability definition. And this in fact here is going to be 2 out of 11. But it turns out this is an idea that we can generalize. This probability is called a conditional probability. It's the probability of an outcome based on some condition that you know has been fulfilled. What is the probability that the sum is 10 given the condition that 1 has to be a 6? The notation would be the following. P of A, you put a vertical bar and you put B. This is, or how it's read, this is the probability of A given B. What are the chances that A will happen given that you know B already happened? The more information you have, the better you are at calculating probabilities because now you know what the actual possibilities are. New information can allow you to update your probabilities, and of course in life there's always new information. You find out something and then you find out something else afterwards, then you find out something else afterwards, and the numbers are going to change on you. And this is what helps us figure out how to deal with that change in terms of what the chances are. Now we saw, basically to figure out this probability, the answer is find the size of the intersection of A divided by the size of B. The intersection of that. Now that is a problematic definition because I mean, we're not going to do it, but it is possible for these sets A and B to be infinity, and then you might have, what does it mean to divide by infinity? It doesn't really make any sense. So we're going to modify this definition with the trick that mathematicians do a lot. Multiply and divide by something that's very convenient. Namely, let's multiply and divide by the size of S. And by definition, what is this? Huh? No, if you see the size of A intersect B divided by the size of the sample space, what's that defining? Huh? That's the probability of the intersection. And what is this defining? Probability of B. Therefore, we have the following. The probability of A given B. What is the probability that A will happen given that you know some other event B already happened? Well, you're going to find the probability of A and B happening at the same time. Then you're going to divide by the probability of B happening. This is an important formula. And this is the formula that defines the conditional probability. Conditional probability is a big thing. Yes.
So S is just S is always going to be like all possible.
Yeah, S is the general sample space when you don't know anything for sure. Like what is all possibilities, no restrictions.
Yeah. So when you
that's always your S.
So when you put a restriction, then you make
yeah, but then if someone says, "Oh, this already happened," that causes a restriction to happen. So now your sample space changes, now your probability changes, and you end up having to do this division to actually find what the actual answer is. And that's what happened in the two children problem, right? Every time I gave you new information about the sexes of one of the children, the answer changed. It's because now this was taking effect. The last few parts of that problem, I was asking you conditional probabilities. What is the probability that there are two girls on the condition that you know one is a girl? What about the condition that you know the older one is a girl, right? That's very different from asking what's the probability of two girls in general. That's not the same thing. And that's why the answer changed on us all the time. We were introducing conditional probabilities, even though I didn't really tell you that's what we were doing at the time. So that's an important formula. Let's introduce an important idea to wrap up here. Now, definition. Events A and B are called independent events. If the occurrence of one does not affect the occurrence of the other. Okay, I run an experiment. I flip a coin and I pick a random card out of a deck. What is the probability that the coin will land on heads? It's a half. Okay, but what if I told you I chose a queen? Now what's the probability that the coins are going to land on heads? It's still a half, dude. Like, the card that you picked has no influence over what the coin is going to do. This is an independent event. Sometimes you're considering an experiment with two kinds of events occurring, but one event has no effect on the other event. We call these events independent events. Now, what does this mean for the conditional probability? So let's say A, B are independent. What does that mean for the probability of A given B? So A and B, nothing to do with each other. What is the probability of A if I told you B already happened and they're independent? It's just probability of A. I don't care that B already happened, it's not going to make a difference. What does that mean though? This is a very important equation, by the way. This is something that you should know in general, but I want to give you another formula. We know that this, by definition, is going to be the probability of A and B divided by the probability of B, right? So here's what we can obtain from that. I don't know if you can see what I'm going to obtain. This means that the probability of A and B, if I were to solve that in the equation, what would I get? Just multiply them. So I get the probability of A times the probability of B. And at this point, I do want to emphasize, I'll put this in red, if A, B are independent, it will only be the case that you can multiply the probability of the individuals to find the probability of and if the events are independent. Now, if you guys are paying attention, you would have noticed that there were multiple times in the past where I asked the question, what's the probability? And someone would say, it's a half times a third, right? Or it's a half times a half, right? It's a quarter. And they were randomly multiplying probabilities. Ever so often I'd say, yeah, that's actually the right answer. And then sometimes I would say, not the right answer. In the situations where I said it wasn't the right answer, why was it not the right answer? It turns out that in those situations, the events had influence on each other. And translates to multiply only if the events are independent. So every time you multiply probabilities and you got the wrong answer, the reason why is because the things you were looking at had influence on the other. So, and translates to multiply if only if the events are independent. So there was a point when we were doing the two girls problem, and I said, okay, if you know one is a girl, what is the chances that the other one is a girl? And the answer was, well, it's 1 times a half, so it should be a half. And the reason why that didn't work is because the events are not independent. The events of having 2 girls versus having a second girl after having 1 girl, one actually has influence on the other. You're more likely to get 2 girls if you already have 1. Right? So that's why the multiplication didn't work in the other ones. But that's an important thing. So this is another equation that I want you to know, but I do want you to realize it does not work in general. Don't randomly multiply probabilities for no reason. If you're going to multiply them, you have to have independence and you have to have and. That's something important. I'll emphasize that next time, but for now, we'll wrap up here. You can try some of the other problems, except example 10. You haven't known enough to do everything except example 10.